Isn't it? Makes it so much better.
So it's just the final? The final statistics.
I can do it.
Yes, you can.
Do it. Do it. Great. Easy peasy. Lemon squeezy.
Okay, so we are starting to talk about polynomials now. In general, a polynomial, we've had this definition, we've seen, it looks kind of ugly, but really all a polynomial is when you're adding or subtracting powers of x. A's here just represents coefficients and numbers in front of x. And then, of course, you have your x's to a power. When I talk about the degree of a polynomial, it is the highest power. Which in this scenario would just be your n. Coefficients are the numbers multiplied with the variables. Bless you.
Thank you.
So in this, that's all of the A's. When I talk about the constant, that's the term without a variable. Which in this would be your A sub 0. The leading coefficient. What?
What's the dot, dot, dot?
Oh, there could be lots of other terms in the middle.
I was just like,
So the leading coefficient is the coefficient of the term with the highest power. Okay, and the example I wrote out would be your A sub n, because n was the highest power. And the leading term is just the term with the highest power. So that's our entire A sub n x to the n term. Okay, so those are all terms. I'm not necessarily going to say write the definition of these, but I'll give you a polynomial and say what's the leading coefficient? How many terms do we have? You know, what's the constant? And you should be able to answer any of those questions if I ask. In this chapter, we are going to be graphing a lot of polynomials. And so we're going to talk today mostly about what the graph looks like, not actually graphing any real specific ones, just talking about general trends in our graphs. When you're graphing these, the graph is always smooth and continuous. You're not going to have breaks in it. You're not going to have corners. It's just a nice, smooth curve. If I wanted to do transformations, all of our other transformation rules still work, so nothing's changed there. The key, if it's a polynomial, all your exponents are whole numbers. It means like 0, 1, 2, 3, and so on. You cannot have a fraction for an exponent, which also means you can't have a variable under a square root. You cannot have a negative exponent, which also means you can't have a variable in the denominator of a fraction. So when I'm looking at a polynomial, every exponent on my variable has to be a whole number. So I want to first just take some examples and see if we can identify if we have a polynomial or not. Does it have this thing? So decide if it's polynomial. If it is, we will give the degree. If it's not, we need to tell why it's not. So the first one, would that be a polynomial? Yes. I don't have any variables in the denominator or under a radical, so it's a polynomial. The degree is the highest power of x. What would that be? 4. Is b a polynomial? Why? It's under the radical, which is the equivalent of saying its exponent is a fraction. Okay. Is the third one? No. Why? No, because there's a variable in the denominator.
It can have a power to it, can it?
Yes. Okay, what about D? Would that be a polynomial? Yes. Now, here's the trick. The degree on this one, 0. That's the same thing as 0 times x to the 0 power, and that's the same as 0 times x to the first, and 0 times x to the second, and 0 times x to the third. I could put any power of x with it and it's equivalent. So can you pick out what your degree has to be there? No, because it could be anything. So what we say, if it is just 0, that has no degree. Because you could put any power of x with it and it's still equivalent. Yes?
If we could put any power, why wouldn't we just like say infinity or something like that?
Degree has to be one particular thing, and so since we can't narrow it down to just one thing, we just say there isn't one.
That's
All right, E, would that one be a polynomial? Yes. Okay, now that degree. Is 8 the same thing as 8 times x? No. What would this exponent have to be for them to be equivalent? Well, x to the first is the same as x, isn't it?
Yeah.
0, because anything to the 0 power equals 1. So if it's a constant other than 0, the degree is 0 itself. Think of it, the degree is telling you how many variables are in it. So if it's just a plain constant, you have no variables, so your degree is 0. All right, F, would this be a polynomial? Yes. Okay, our degree. The definition I gave you for degree was the highest power as long as everything was all multiplied out. So I have to think about, if I multiply this out, what would my highest power of x be? I have an x cubed here, and I would have an x squared here. So altogether, how many variables would be in that? 5. I have 3 x's here and 2 x's here, so that's 5 x's total. So this one would be degree 5.
So you would add those?
Yes, because if we actually went through and multiplied this, you would have negative 2x cubed. If you squared that, you'd write it twice in FOIL. And then when you went to distribute, since the x is written each time, you would add those exponents. All right. Questions there? What I want you guys to do, I gave you some grids. I want you to take a quick second, use your graphing calculator if you want. Just draw me a very rough sketch of what these things look like. So x cubed, you graph it, and it's just your chair. How does x to the fifth compare?
Same thing, just like skinnier.
Right. Just a skinnier version of the same thing. Okay. X to the fourth, what does that look like?
It's just a U.
Yep, just like a quadratic. What about x to the sixth?
Same thing.
Same thing, but it got,
Smaller.
yeah, just got a little skinny. Okay, so Ava's already noticed the pattern. What was your pattern?
That the even numbers were like a quadratic and the odds were the chair.
Yes. So we can look at a polynomial and decide what it's going to look like just from your degree. So it will resemble x squared if the power is even, and x cubed if the power is odd. The thing that changes is the larger the exponent, what happens to your graph?
It's skinnier. Narrower.
You could put it gets skinnier. Okay, this is getting us into the idea of end behavior with the graph. End behavior tells us what is going on at the ends of the graph. So when the x is really big or really small, which direction is it going? It is determined by your leading term. When looking at that leading term, you have to pay attention to two things: the coefficient and the degree. If it has an even degree, think about our quadratics. We knew something about the quadratics. If it was a positive, what did the graph look like? It opened up. If it was negative, what happened? It opened down. So what we are going to say is the leading coefficient is positive. I'm going to ask you for end behavior. You can just draw me two arrows. You can say up, up. Both ends are going up. If it's negative, my end behavior would be down, down. Both ends are pointing down.
There's literally one of them. Right, one up and one down.
Not if it's even
Oh.
degree. So like an x squared and x to the fourth, those we wouldn't. Those ends will be doing the same thing. The Math Excel textbook, if you looked at those, they are going to say something a little different. They're going to say as x goes to infinity, f of x goes to infinity, and as x goes to negative infinity, f of x goes to infinity. And that's just more time consuming, I think, than we need to be. If we can just draw two arrows and get our point across, that's all we're going to do. So just understand, you could see it written in terms of infinities telling you, your x is getting really big and your y gets really big. But we're just going to draw arrows. If the leading term has an odd degree, then we said it was going to look like x cubed. So if it's positive, we know x cubed looks like this, so what's my end behavior? We go left to right though, so we'll call it down up. Okay, so then if I flipped it, we know a negative just flips the graph, so what would this end behavior be? Up, down. All right. So we're just going to practice finding end behavior now. Okay, if I want you to find the end behavior of this, what are you looking at? Which part are you concerned with? The leading term. A lot of times that's the first term. It doesn't have to be though. It's just the term with the highest power. So that is all I am going to look at. Then, looking at that, we know an x cubed means it's going to look like a chair. It's a positive coefficient, so it looks like the regular chair, so your end behavior is? And that is all you have to do. Okay. If I have negative x to the 6th, I'm looking at this term. The x to the 6th, that's an even power, so what does that tell me? It's a parabola. The negative will do what? Make it upside down. So my end behavior is?
Down.
Down, down. Okay.
Does this one matter? Is it the same?
We have to think about if we multiplied it all out. To find the leading term, that's when everything is added and subtracted. If it's in factored form, you have to multiply it out. But we can do this quickly. We don't really have to multiply out everything here. All I need is my leading term, correct? So if I did that, you're just basically taking your highest power of x. You'd have a 3, you would have an x. This one you would end up with an x squared. So if you multiplied those, what would your leading term be? 3x cubed. So x cubed is odd, that means it's looking like a chair. 3 is positive, so it doesn't flip it, so my end behavior is down, up. Yes, Ava?
So it doesn't matter, we just have to get the like terms together.
You have to multiply basically the highest powers of x.
So if there was like in A, if there was another x cubed,
Uh-huh.
we put those together.
Yep,
and get
if they're
this.
multiplied, yes.
If we don't add them
No.
together, just multiply.
Okay. This one. It is multiplied, so I have to think about what would my highest power of x be. So I have a 1/2. This parenthesis would give me an x squared. This one, if you have an x squared cubed, that becomes x to the, if I have an x to the 4th, so if I put all those together, I get 1/2. I have 2, 6, and 4 x's, so it's x to the 12. So it's a positive, even coefficient, so it looks like parabola, so my end behavior is up, up. Now, let's say you were doing this and you just got confused on multiplying it out. Is there a way to determine that end behavior? Graph it. You have a graphing calculator, don't you? Could you plug that in, look at the graph, and tell me which way the ends are pointing? Absolutely. So use that to help you if you need
We
to.
don't really need to show much work on that because we could just graph it.
You could. It will be faster as we do problems if you don't have to, but yes, use that to check yourself. Okay, so let's try a matching. See if we can pick out which graph would be which. So the first function, the f of x, what would the ends have to look like on that? Up, up. So which one would it be? Okay, g of x, what are my ends going to look like?
Down.
Upside down parabola, down, down. So it would be A. Okay, the next one, what's this look like? Regular chair, down, up. So that would be B. Last one. What would it be? D. It's a chair flipped, so it's up down. So that's D. Okay, so you can now use your behavior to kind of pick out which graphs are possible. Few more things that we need to mention. Turning points are where your graph changes direction. Those are going to be maximums and minimums on a graph. So for instance, if I gave you, let's say this function. How many turning points does it have? How many times does it change direction? 3. 1, 2, 3. So does everybody understand what a turning point is? Okay. Extrema, that is another word for the max and min. So you might be asked how many turning points does it have? You might be asked how many extrema does it have? I'm asking the same thing. Where does it change direction? Where do you have maximums and minimums? There is a difference between local and global maxes and mins. Sorry, I used absolute this time. Absolute and global mean the same thing. This is the actual highest or lowest point the graph reaches. Does this one have an absolute max? A highest point that we ever get to? Yes, this would be our absolute max. Does it have an absolute min?
Yeah.
This is a min, but doesn't my graph get lower than that on the ends? So this one does not have an absolute minimum. Okay, local maxes and mins are just higher or lower than the surrounding points. So this graph would have 2 local maxes. This is a local max because it's higher than those around it. This one would also count as a local max because it's higher than those around. How many local mins do we have? Only 1.
So when you ask us about it, we have to label all that point can be?
Yes. We're really not going to do a whole lot of that quite yet, but I'm just trying to get you familiar with all the terms that we're going to see. Okay. Let's talk, look at an example and try to classify some of these. So using our terms. So this isn't the one I put on yours. I did this one. Okay. So, local extreme points of F. So that's the first one. Where would I have a local max? CD. Where do we have a local min? EH and AB. Okay. Same thing for the next graph. For G, what's my local max? MN. Local min is JK. All right, second question. On either graph, do we have any absolute max or mins? Does F have an absolute max? Okay, what does it have? Has an absolute min at where? G, does it have either? No, because this keeps going up forever. That end keeps going down forever. So it does not have any absolute maxes or mins. Alright. Last thing I want to mention. We're going to talk about turning points. Turning points, as we just said, is where your graph changes direction. It's actually related to the degree. If your degree is 5, then you can have 4 turning points at most. You don't have to have that many. So if my degree was 7, what would be the most turning points I could have? 6. You don't have to, but that's the most. Likewise, if I look at the number of turning points and I see a graph has 5 turning points, the degree has to be what? 6 or more. If it has 3 turning points, my degree would have to be 4 or more. Okay. The x-intercepts of a graph, we know x-intercepts are where you cross the x-axis. Another word for those are your zeros. And it's related to your degree. When we graphed a quadratic, how many times did it usually hit the x-axis? It could hit it, right, 0, 1, or 2 times. So the most was 2 because it was degree 2. So if something was degree 4, how many times do you think it could hit the x-axis? 4 times. So the x-intercepts, at most, the x-intercepts are the degree. Or maybe I should say the number of x-intercepts would match your degree, at most.
So they can be that degree or less.
Yes. Okay. All right. Last thing, and we will talk more about this part next week. We're just going to get it down on our handout. With our quadratics, sometimes we solve something, we would get a multiplicity of 2. That means that x-intercept worked twice. The multiplicity impacts the shape of your graph. If you have an odd multiplicity, so if you have a 0 and it has an odd multiplicity, then what happens is your graph will just go through the point. So if I find a 0 and it has a multiplicity of 1, 3, 5, 7, my graph is just going to hit that and go through it. If you have an even multiplicity, so if it's 1 multiplicity 2, what happens is our graph hits it and it bounces back up. So even multiplicities bounce, odd multiplicities go through. That is the end for today. We've got about 8 minutes. I have posted a handout on Classroom. It should be fairly quick. The first ones are just asking for end behavior. So just drawing your 2 arrows. Second ones are asking you how many turning points, so it's just 1 less than the degree. And then the end, they ask you questions about some graphs.